So we're talking about exponential growth and decay still, now applying it to some more word problem, to some more, real life examples. I told you guys about the bacteria, and now here's a couple more examples. All right, so we're gonna start first by the most common use of exponential functions, and that's compound interest. All right, so let's talk about what compound interest is. Compound interest is when you have money in the bank and, the bank is going to pay you interest on this, fine. But the way it works is, let's say, 3 months later when they're closing out their statements, they pay you interest, okay? So suppose you start out with like $5,000 and then afterwards they pay you interest and now you have like, I don't know, $5,004. The second time they're going to give you interest, they pay you interest on the whole amount, not just on the initial amount, okay? All right, so the formula for this is this. So it's AP 1 plus R over N to the power of NT, okay? You've done this in algebra 2 or intermediate algebra. Okay, so let's talk about the variables used in this. First, you have A, right? And A is the final balance in the account. So when you get your statement at the end of the 5, 6, 9, whatever years, how much money do you have in there right now? P is the principal, which is the money used to start the account. So when you went to the bank to open up the account, how much money did you put in? R is the rate, but it's got to be in decimal form. And how do we put the rate in decimal form? You divide by 100, or you move the decimal point over to the right, to the left twice.
Left or
right? Left. So if it's 5%, okay, the decimal point is here. You move it to the left 2 times. Okay? All right, T is the time in years. N, this is the important part. N is the number of times within a year that you are paid by the bank, okay? And that depends on the type of account that you've signed up for. So if it says that interest is compounded annually, if you see the word annually, how many times in a year is annually? Once. That happens once a year, right? Semi-annually means how many times in a year does that happen?
It's like 4 times.
Twice. Semi-annually.
That's quarterly.
Right. Semi-annually is twice. Half a year. Semi means half the year. Quarterly, how many quarters in a year? 4. So N equals 4. Monthly, how many of those in a month? 12. Daily, 365.
I mean,
Okay?
if it's leap year, then there's 66.
Right.
All right.
We're not going to consider leap year. And then one thing I didn't put on here, I guess, is weekly. I get asked every year weekly. How many weeks in a year?
I don't know, 12 times.
So it's 52 weeks in a year.
Oh,
Okay. All right. So take a look at this one. This lady, Mrs. Algebra, invested $2,000 into an educational account for her son when he was an infant. The account has a 5% interest rate. If Mrs. Algebra does not make any other deposits or withdrawals, what will be the account balance after 18 years if the interest is compounded as follows? So we have 3 situations here.
This section just took so what will give you the higher?
Yeah, I agree with
Okay, so
I'm gonna fail this part. No, it's just the formula.
okay, so let's write down everything that we have. This 2,000 is how much she invested. So which of these variables is that?
P.
That's P. The account has a 5% interest rate. You move the decimal point over. R is 0.05. 18 years, that's T. Okay, now here it says this is being compounded quarterly, so that means n is equal to 4. So now, each time you do this, to show me the correct amount of work, I want you to write the given, and then I want you to write the formula. A equals P, 1 plus R over N to the power of NT. This is you know this. Okay, so P, at this point, it's just plugging things into the equation. So 2,000, 1 plus 0.05 over N, which is 4, to the power of 4 times T, which is 18. Okay, so we go to the calculator. Okay, when you go in to put this in your calculator, I need you to be able to do this in one shot. Okay?
Oh, really?
Yeah, because of 2 reasons. A, transferring just adds to mistakes in the intermediate steps. And then also, often you get rounding error, which we also don't want. So,
This calculator is pretty good.
I got it.
okay, so here's what we're going to do. Before I take answers from you guys,
Are we rounding?
it's going to be 2,000,
Oh.
1 plus 0.05 over 4, close parentheses here, to the power of 4 times 18. Right?
Yeah. Yeah, I get that.
Okay,
We
so
Sorry.
it has to look like this, right? So make sure that it looks the way you had it on your paper. So area, I'm sorry, not area, but A is equal to 4,891. Okay, so now this is in money, right? This is in dollars.
You make that 4 times a year.
Hang on. This is money. So it has to have dollars and cents. You have to go to the correct 2 decimals. So 0.84. Now, if you write you have to write the formula. Oh my gosh.
Sorry.
You have to write the formula once for each problem, right? You have to. I'm going to be looking for that. And then here, it's 2,000, 1 plus 0.05. Now, monthly means n is 12. So over 12 to the power of 4 times 12. Okay, here, look up here for a minute. When, sorry, it's 12 times 18. NT. Okay, now look at what I want you to do. Everybody look up here for a minute. I need you to press the up button once, twice, until you get this back.
Oh, I did it.
Press enter to get it back. Now all you have to do is just edit the 2 things instead of typing the whole thing again and making a mistake because you're rushing. So here, you gotta do 12. And here, 12. Okay, so now you have $4,910.02. Let me just give me this one's being compounded daily. That means n is how much? 365. So A is going to be 2,000, 1 plus 0.05 over 365 times 365 times 18 to the power of. So again, I bring this back and I'm just going to edit. Yeah, this is why you paid the big bucks for this calculator, right? So you could minimize your mistakes and you can maximize your efficiency. So you would think, oh my gosh, now like the bank is paying me interest every single day. And you think you're just going to make so much more money, but it's $4,918. And do I just put 9 here? 90. Okay, dollars. All right, so look at what happened. Here you were being paid 4 times and it was 4,891. And here, you know, it's 918. So over the 18 years, right, the difference between being paid monthly and daily is $8.88. $8.88 over 18 years, right? So look at that. So that's how the function works. That's how this formula works. Whereas you think it's just going to grow forever, but it levels off. Okay? All right. Now, this woman, what if you find an account that doesn't pay you quarterly, monthly, or daily? It pays you every single millisecond of every single minute. So right now, paid you again, like it's just paying you interest continuously. That's a thing. That's a big thing. So this is the continuous compound interest formula. That formula is e to the RT. Okay? Where does it come from? You know how in this formula you had 1 plus r over n to the power of nt? For those of you, okay, remember what we did yesterday? Look. We said if you have 1 plus 1 over something to the something, that just becomes e. So, okay, so here, 1 plus 1 over something, that just becomes e. Okay? So that formula will just be e to the RT. PE to the RT.
It's like the same thing, kind of.
Kind of, but now interest n is not 12 or 365. N is infinity now. That's the thing.
Oh.
So Mrs. Algebra went shopping. She found an account that pays 5% interest, but this time it's compounded continuously on the same investment. She is making so much money right now. So let's see. A is P, e to the RT. P is 2,000, e to the 0.05 times 18. All right, let's go back to our calculators. 2,000, e is here. It's on the left-hand column here, right there. E to the, what was it? 0.05 times 18. Oh my gosh, let's see how much more money she's going to make. Wow. $4,919.21. So look at that. The difference between her getting paid daily and continuously over the 18 years, it's not even $1. It's like 30 cents. Because this is 0.90, so it's 31 cents. She gets a whopping 31 cents more over the 18 years. Okay? So the reason for that is, eventually, like, this doesn't increase forever. Remember, we said E sort of levels off, and that's sort of what happens. So that's, yeah. Yep. So that's that. Okay? All right, now, these formulas for compound interest are actually variations of more like generic, more general mathematical formulas that bankers have just, and like investment people, they've just taken it and they've put in variables like P to stand for, what they do. These formulas actually come from like a deeper, more umbrella sort of a formula, because this exponential stuff doesn't just apply to investments. It also applies to populations of people, animals, bacteria, amounts of radioactive material, right? All of these follow exponential growth and decay rules. Okay, so these are the two types of formulas that apply to pretty much everything in life. And we're going to go over them right now. So we have exponential growth or decay, right? And the formula is this. N equals, okay, this funny little thing is N naught. So that symbol 0, it just means initial. we call it N naught. So rather than using different letters for initial and final like A and P, we just say, okay, N is the final, N0, and naught is the initial. Okay? So, yeah, it's a universal notation. So N is final and not initial. R is the rate again in decimals. T is the time. Okay, now, if the quantity is increasing, we use positive R. If the quantity is decreasing, we use negative R. That means if the population is increasing, we use the formula as you see it here. If the population is decreasing, then you just do N equals N naught 1 minus R to the power of T. Does that mean you're going to memorize two different formulas? No, just know that, okay, increasing plus R, decreasing minus R.
And it'll tell us if it's
Yeah,
right.
of course. Okay, when do we use this formula? We use this formula for problems involving quantities which increase once a year only. For example, rent, salary, right? And so on. Okay? All right. Then we have continuous exponential growth or decay. Again, we have N equals N naught, same thing, but now it's e to the kt. Okay, what the heck is this k business? K is the same as R. In the continuous formula, math and science uses K, and then in here we use R. Right. Well, it's a rate. It's still the same as R. It's not the K constant in chemistry.
Oh, okay.
Yeah.
Is this the formula that like it won't increase by a lot, but it keeps like multiplying itself by the number of like in like a long period of time it'll make tons, like it'll make tons more.
Like you're talking about money?
Or it's in general, because like it gets the
If it's increasing, we use positive K. If it's decreasing, we use negative K. So for example, we'll do N equals N naught e to the negative kt. Okay? When do we use this? We use this when something increases or decreases continuously. You will have that word in the problem. Okay? So population, radioactive decay, half-life, and so on. But it'll specify in the problem. Okay. So again, in case you forget what the formula, what the variables in the formula meant, R and K are the same exact thing. You see that? It's just the rate, and remember to divide by 100. And the time is usually in years. You just have to know and be consistent. Okay. A state population is decreasing at a rate of 2.6% annually. The state currently has a population of approximately 11 million people. If the population continues to decline at this rate, predict the population of the state in 15 years or 30 years. Okay, first let's write down what we have. 2.6% annually, what is that?
Rate.
That's your rate. Okay, so first of all, am I going to use the first formula or the second formula? Does it say it's continuous? Is there a word no, so we're going to use the first one. No, but it doesn't say it's declining continuously or it's a whatever. So, okay, so we're going to use this one. Okay, so let's write down everything that we have. N is what we need. Do we have N naught?
Yeah.
How much is it? Okay, it's 11 million, and I'm just going to write it like that for now. Do we have R?
Yeah.
0.026. Do we have T?
yeah. Oh. Yeah.
It's this one. It's 15 years. Okay, now here's the important part. It's here. It's in the part of it's the question here. Okay, so N equals, okay, 11 million, right? We just put 11 here. We don't do all the zeros. But we know that we're talking in millions. Okay, so this will come back in a minute. And then we have 1. Okay, is it declining? It's declining. So it's going to be minus 0.026 to the power of 15. So n is 11. No. 1 minus 0.026 to the power of 15. Okay, that gives me 7.4. So does that mean there are 7.4 people in the state?
7.4
Million. Okay? So right, you will just, okay, so hang on. So we got 7.4, so we say 7.4 million people. Okay, 2 things. As far as the rounding, go with, on the test or the quiz, go with what I've specified. I will say round to the nearest whatever, and you go with that. 2, well, I guess I have 3 things to say. 2, when you give me the answer on the number line, 7.4, wrong. 7.4 million, half right, because I want to know that you are talking about people. So say it's 7.4 million bacteria, or rabbits, or people, or foxes, or whatever. 3, and I say this again, I was talking about this a little bit yesterday. I say this to my own children when they're doing math at home. At the end, ask yourself, does my answer make sense? Because this population is declining. We started with 11 million people. So if you get an answer of 20 million people, that does not make sense. What have you done? What have you done? What's the first thing? You probably did plus R here instead of minus R. So go back and check, all right? At least, the direction of the, increase, decrease should be right. Often, like, it's a compound interest problem, and then people end up with less money than they started. That's not cool. So you want to go back and fix it. Okay, so this one, it's the same thing, but in 30 years. So here, again, I just edit. Don't retype everything.
I think it's plugged in. You have a
4.9907.
I think she has a calculator and it's plugged in.
So look, I'll tell you. So we got 4.99, so it's approximately 5 million.
We have to do like the approximate sign.
No, you don't have to. I just do it because it's an approximation. This table shows the number of reported cases of chickenpox in the United States in 1980 and then again in 2005, right? Okay. So again, this does not tell us that it's increasing it says it's decreasing at an exponential rate, but not continuously. So again, we're going to use the same formula of 1 plus or minus r to the t. So it's going to be n is equal to n naught 1 minus r to the t because it's decreasing. Okay? Okay, now look at what this says. Identify the rate of decline and write an exponential equation to model the equation. So it says identify the rate. That means we have to find r. Okay? So what do we have? If we need r, then we should have all of the other pieces of information. So do we have okay, so do we have n? That's the final. How much is it? 190.9. The final n. 32.2. And look, this says it's in the thousands, so later on we're going to use that. So it's 32.2. And what about n naught, the initial? 190.9. I also need T. How much is T? From 1980 to 2005, how many years? Well, from 1980 to 2000, how many years was that?
It's like 30.
20. From 80 to 2000 is 20, 25 years. Okay, so now I need to find R. N equals N naught. 1 minus, what's R? That's what we need. To the power of 25. So we're going to divide by 190.9 first. Okay. And, okay, so look. How much will that be?
1.6.
I got 1.16. Yeah.
Okay, so look at what we're going to do. 0.1676. Put as many decimals as you can. Equals 1 minus R to the power of 25. Now, how am I going to get rid of that exponent 25? This, you have to go back to your algebra days. So you have to do the root, but it's the 25th root. So here, 25th root. Okay, so luckily we have to do that with the calculator. But now, with the calculator, here's what you do. The 25th root, in order to do it, it's control and this button here. Okay, so control this. Now look, wait, look. In here, in the index, you put 25. But in the inside, don't type in any numbers. Here's what I want you to do. You can put in the whole answer in there. So you do control, answer, that's that negative button, right? That means it's not rounding for you, and you're not rounding, and you're not you're not typing incorrectly. It takes the whole answer, so it's the most precise answer we can get. Okay? Enter.
0.9.
So 0.931 is equal to 1 minus R. Now what am I going to do? Not minus 1. Minus 1. So negative R is equal to, so here again, I just do minus 1. I'm not retyping anything. Negative 0.0689. So what's R?
0.0.
Okay.
Wait, you got a different, a little bit different. 32 instead of 32.
Oh, I did?
Yeah.
Oh, I shouldn't have.
It's the same. It's really close to the same. Instead
Okay.
of 1676, it's 1686.
And then what about the R? Okay, well, fine. So now, yeah. Okay, so, but now look at what it's asking us for. It's asking us for an exponential equation to model the situation. If you want an equation, you need variables in your equation. So the equation is this. We started with this, right? In the equation, if you want to write an equation, this and this must stay as variables. All right? So I have n equals, that stays as an n. N naught, that's the initial. What do I put in for the initial? 190.9. 1 minus, the R is 0.0689 to the power of T.
That's the answer.
Yeah, that's the answer. So look for what you are asked for. You want an exponential equation. If you want an equation, you have to have an equation. All right? So now it says graph the equation and use your model to predict when the cases will drop below 20,000. Okay, so let's graph this now. We're going to graph the equation that we just created. So here I get a graph.
Oh, graph on the top.
Yeah. We get 190.9. 1 minus 0.0689 to the power of t, or x.
1 minus.
Okay.
Wait, so I got 7 and you got 0. I got, because you put the 32 and not the 32. Your last number in the 0.1.
Okay, what is your number? It's 0.0.
0.6.
Okay, next. When you press enter, you see nothing. Okay? Here's the reason why you don't see anything. These numbers, first of all, the year is going from like
So far.
0. Oops. The year, do we want negative years? We don't.
We don't.
It's going to start at 0 and go above. Maybe like, I don't know, we want to go like 100 years, whatever years. Let me finish this and then I will take everybody's questions. The Y represents how many cases. So look, here we have 32.2 thousand, 190.9 thousand. So that's where we started and it's going down, correct? So I want to go at least 200 here. So let's go to menu. Number 4 is window, and number 1 is window settings.
I see.
Cool. Let me do this. So here, 0. Guys, fix your windows here. X max, so 100. And then 0 to 200 for Y. Because you just sort of have to see what are your Y values. It's going like between like 190 and 32. It's starting at 190 and going down, right? So enter. So this is what it looks like. Okay? Yeah. Well, no. Yes. So it says graph the equation and use your model to predict when the cases will drop down. So when you're going to graph your equation on graph paper, okay, what did we do here? We went from 0 to 100 for the x-axis. So here I go in tens. $60, $70, $80, $90, and $100. Here I went to 200, right? So I could go up by 20s. $20, $40, $60, $80, $100, $140, and so on. Okay? Now, how are we going to graph this? All right, I'll show you. When you go to menu and you say trace here, menu 5 and 1. Okay? It gives you this. So now what I can do is, it's really, really cool. Suppose I want the value when x is 10. I just type in 10, enter, and it's 93.5. Okay? So when x is 0, this was, where did I start? I started at 192. When x is 10, it's 93.5. Okay, so what about when x is 50? Just type in 50, enter, 5.38, all the way down there. What about when x is 30? 22.4. Okay? So there I graphed it. Now it says predict when the cases will drop below 20,000.
So is that the asymptote?
There is an asymptote, yeah. But it says, when will it drop below 20,000? Where is 20,000? 20,000 is right about here. So look, we could do it a couple of ways. When does the y hit below 20,000? It's somewhere between here, but I can't really guess that. Look, now the y is 24, 23, 22, 21. Right about there, it's 20.9, 20.1, and then 19.4. So you see how it's between 32 years and 31 and a half years. Okay? To know more precisely, go back to tab, hit, okay, so press 20, enter. So look, that's the line, right? So where was it? Where did we say it was? It was around like, what was it?
19.
But the year was around like 31, right?
Can we go menu?
So we say 31 years. You do menu, trace is number 5, and number 1. So 31 years, it means if we started at 1980, right? We started in 1980. How much is 31 years after 1980? 2011. Okay. All right, and with that, it's time. So this homework from the book is due Monday. And remember, it'll be turned in Monday along with the other assignments.